So last time we talked about the problem of overpumping. The simple conclusion is if your pump is too strong, maybe you will suffer from the multi-pulsing issue. That means for each round trip, there might be more than one pulse. And if you use the graphical solution, it means the two nonlinear curves might not have intersection or solution, unique solution. And another way that you can envision there is multi-pulsing is imagining your pump is fixed while your pulse is split into two pulses. Then each pulse will share only 50% of the energy. So your peak power will be reduced while your gain is maintained. And we know the red curve, H curve, is about loss saturation. Blue curve, F curve, is about gain saturation. So that means the blue curve is unchanged, while your loss curve will be lowered. And there could be a crossing point under this situation. So multiple pulsing is possible. Okay. Another interesting issue is the impact of self-amplitude modulation coefficient gamma. So here I show you the original graphical solution. Okay, you have a red curve, H curve, blue curve, F curve. Probably you can have two intersection points, and only the stable solution is marked. Okay, the left intersection point is stable solution. Then what happens if you increase the gamma coefficient? Gamma is the SAM coefficient, self-amplitude modulation coefficient. Do you still remember the meaning of SAM? It is the pulse shortening effect of this passive Molag laser. The higher the laser power with a positive gamma, that means your loss is smaller, okay? And the gamma is the proportional constant. The loss coefficient, the change of loss coefficient is proportional to gamma times your laser power, okay? So intuitively, bigger gamma could be advantageous because that means you have stronger pulse shortening effect, right? But let's see what would happen. When gamma is increased, then your H curve rises. H curve is the red one. And as you might have remembered, H curve means the loss saturation. Okay? So if your gamma is larger, H curve is proportional to gamma. So larger gamma means larger H curve. So you can expect the red curve will be raised. Okay? And your F curve is governed by this relation. LC plus L0, just the constant, minus your saturated gain, G. G is a function of A0. And this curve will drop as gamma increases. Why is that? If you check the formula about saturated gain, it's equal to small signal gain, G0, over constant 1 plus average power over saturation power, where your average power is proportional to square root of gamma and the inverse, okay? Where does this relation come from? You can review the equation 2 when we try to solve the master equation. We assume the solution is a second hyperbolic function, right? With two unknown constants, A0 and the TP. Substituting the second hyperbolic function into the master equation, we got two algebra equations. equation 1 and 2. If you check equation 2, you can arrive at this result. Your average power is inversely proportional to square root of gamma. Okay? So if gamma is bigger, average power is smaller, and you have a smaller denominator. Then your G, your saturated gain is bigger. Okay? But remember, there is a minus sign here. Okay? So a bigger G means a smaller F. So your F curve actually drops as gamma coefficient increases. So the blue curve will drop. Okay? So the analysis is like this. If you increase gamma, the red one rises, the blue one drops. So what happens? You might have something like this. Okay? And how about the intersection point? Okay? You can go back and forth. Okay? Then you can see this cross-section point, intersection point, actually moves to the right. Okay? So it means steady-state pulse becomes stronger and shorter. Okay? Stronger because now the intersection point corresponds to a larger A0 because it moves to the right. And the relation between amplitude and the TP implies the steady-state pulse must be shorter. Okay? So to some perspective, it is a positive thing, right? If you increase your SAM, you got stronger and shorter pulse. Okay. But what is the price for a larger SAM coefficient? Could you predict by observing this graphical solution? 有好处，你得到更强更窄的脉冲。那有没有坏处？
More likely to have multiple pulses.
Why?
Because the two curves might go off and have multiple.
Oh, you mean if it keeps on going, eventually these two curves might no longer cross with each other? Yes, it's right. Multiple pulsing could be more possible. Or in other words, you see the stable solution moves to the right for sure. How about the unstable solution? The right crossing point actually moves to the left. Okay? So it means the range between these two intersection points shrinks as your gamma coefficient increases. Okay? When these 2 points bump with each other, that's the limit, right? Your laser is no longer stable in that case. So a bigger gamma coefficient actually gives you a less stable laser, okay? So that's the price you have to pay. It's now not always positive to keep on increasing your SAM coefficient, although initially it can give you a better result, shorter pulse, stronger pulse, but it will eventually destabilize your laser. Okay, then the next question is, could you use the similar analysis method to predict the impact of pump? What happens if you increase your pump? Okay, I just demonstrated how to use graphical solution to analyze the impact of SAM coefficient. Could you use the similar skill to analyze the impact of pump? Or simply speaking, what happens to these two curves if you increase your pump? Remember, one curve, the red one, is about loss saturation. The blue one is about gain saturation. If you increase your pump, what will be increased? Gain or loss? Gain, right? The stronger the pump, the larger the small signal gain. So the gain saturation curve will change with the pump. And how about the loss saturation curve? Basically unchanged. It's up to your laser pulse, right? It's a fast saturable absorber. It's independent of your average power. It's about your peak power, right? So one curve does not change. The other curve will move up or down. And you can predict how does the intersection point move. Moves to the right, it means you got stronger and shorter steady state pulse. If it moves to the left, you got the reverse. You got weaker and broader steady state pulse. You can use this simple graphical solution to predict the behavior of the laser whenever some parameter is changed. Okay, so this is a very useful tool. Okay, although this is not the only way you can have the solution. You can just rely on algebraic solution. 直接去解，你会得到答案。但是如果你不使用这个图，你就不太容易去预测每一个 parameter 对最后结果的影响。Okay, so that's the value of graphical solution. It helps you to have an insight about the characteristics of the laser. Okay, we can move on to the third section, passive Molar-King with both amplitude and phase modulation. So we will start with the master equation and the corresponding solution, followed by some discussions. So let's start with the assumptions. All the assumptions we have to make in this section. The first 1, 2, 3, 4 are the same as we did in section 4-2. Okay, you have fast saturable absorber, you have weak loss saturation, slow gain, and weak gain saturation. Everything is the same as before, but the last three are different. Now we assume there is dispersion. The GDD parameter, big D, can be either positive if it is normal dispersion or negative if it is anomalous dispersion. We assume there is cell phase modulation, so delta coefficient is positive. It's always positive, assuming N2 coefficient is always positive. You might have some non-zero CEP shift, so constant phase shift psi can be non-zero. Okay, so the last three are new, different from the previous case. So go back to the original complex master equation. It's written here, okay? And remember, according to our assumption that gain saturation is very weak, so G of T is a constant G. Okay, we forget about the dynamics of gain. And if loss is pretty weak, then dynamic loss L of T can be modeled by L0 constant minus gamma coefficient, the SAM coefficient we just mentioned, times the laser power, P of T. And the psi CEP phase shift, delta, cell phase modulation coefficient are non-zero, so they have to be preserved. Besides, your dispersion is non-zero, so big D parameter is non-zero. It's still there. Okay. Then this master equation, actually complex master equation with real part and the imaginary part, can be reorganized into this case. Okay. Just combining G, L0, LC together. G, LC, L0, and CEP phase shift together, you got this. You can combine the SAM, self-amplitude modulation, and the self-phase modulation together, you got this. Okay. So this is the reorganized master equation. And be careful, G is not an independent constant. The formula is here, related to average power, and the average power is related to integration of your absolute square of A of t. Okay? So actually, G depends on the unknown function A of t. Okay. L constant is a given constant. It's equal to LC plus L0, or the loss seen by the pulse wings. Okay? Because at pulse wings, virtually no laser power, so your total loss is simply a constant loss coefficient, LC plus L0. If you substitute P of t equals 0, this term disappears. So you have a total loss like this. Okay. And in addition to saturated gain, G, the CEP phase shift per psi, and the P of t is actually absolute square of A of t. These three parameters are unknowns, right? They are not given constants. Although it looks like A of t is the unknown function, but P of t is its absolute square. So this is unknown. CEP phase shift, in the beginning, we have no idea what's the phase. So this is an unknown to be solved. G is related to P of t like this. Okay. So this is not a standard linear ordinary differential equation. It is a highly nonlinear differential equation.